Hello, everybody. Thank you so much for joining us today for another exciting tinyML talk. I'm your host. My name is Daniel Sitanaika. Today we have a really awesome talk on binarized neural networks on microcontrollers, and that's from Lukas Geiger from Plumerai. So thank you very much for joining us today, and let's go through some of our introduction. So first of all, I want to give huge thanks to our tinyML talk sponsors. So first up, ARM, who are our tinyML strategic partner. Then we have DeepLight, Edge Impulse, where I work. I got my t-shirt on. Maxim Integrated, Kixo, Reality AI, and SynSense. And if you'd like to be a sponsor of the tinyML talks, send an email to betty@tinyml.org to get some more info. Our next tinyML talk is going to be on Tuesday, February the 2nd, and that's from Martino Sobaro, who's an R&D scientist at SynSense. And his topic is going to be always-on visual classification below 1 milliwatt with spiking convolutional networks on Dynapse CNN. So if you'd like to give a talk with the tinyML talks, please contact talks@tinyml.org. Just send us some information about what you'd like to speak about. So to introduce Lukas Geiger, Lukas Geiger is a deep learning researcher at Plumerai, working on new training methods and architectures for improving accuracy and efficiency of binarized neural networks. He's the author of the open source Larq training library and core developer of the Plumerai software stack for deploying BNNs on embedded platforms. So I'd like to hand over to Lukas to take it away.
Thank you, Daniel, for the great introduction. Yeah, I'm happy to talk to you about binarized neural networks on microcontroller. I'm happy that you all joined. And I think in this audience, I don't need to explain why tinyML is a good idea, running machine learning models, running ML on embedded devices can unlock a multitude of different applications and can truly revolutionize both everyday lives and applications in the enterprise. But if we have all of these great benefits, I want to start with a question, and why is that tinyML not already everywhere? So the first reason for this is actually the feature why we are all very excited about tinyML. It happens under a very, very constrained computational budget. And this means that we are always battling with the trade-off of accuracy and latency and memory footprint. And which means that currently tinyML is usually mostly happening on quite simple tasks with recognition on sensors, machine learning on sensors, whereas for larger problems like computer vision, it still has some way to go. So bringing a tinyML or an embedded machine learning product to reality requires many different skill sets within a company and within teams. And this is why I'm very happy about this community, that we are able to talk here about tinyML and bring different people together to discuss and move the field forward. So to you, it's probably no surprise that the road ahead, machine learning is really taking off, and well, it has taken off, it's booming. There are many tens and hundreds of papers submitted each day to the machine learning category in archive. And with that comes machine learning and deep learning to many different use cases, which get increasingly more complicated and require an increasingly larger amount of compute, both for training and also for inference. So I want to take a bit of a step back and take the view of machine learning or a product team in a company. We have something developed, it is working great, it gets nice results, but it's computationally way too expensive to actually bring on the device. So what can we do? So the first probably obvious idea to most of the people like me who are coming from research is to get more hardware. Buy a new CPU, buy a new GPU. This in the real world, this is often not possible. This comes with larger power costs. It would result in also just more cost from those hardware being expensive. And if we look into the future and ask ourselves 2 to 5 years, will we still have this problem of resource constraintness? And the answer is yes, of course. So Moore's law is slowing down, which means we're seeing a trend to even more specialized hardware, GPUs, TPUs, FPGAs, also in the embedded space. But even if Moore's law would happily go on and then out scaling as well, the increasingly power-hungry algorithms that are used today would still, I think, outpace all of that. And so we need to do something more on the research side and actually look at our ML algorithms. There have been in the latest years many great advances in efficient model design, the mobile nets, efficient nets. All of those type of algorithms have hugely impacted what's actually used by practitioners. But we can also go further and do quantization, do knowledge distillation, pruning. There are a multitude of ways to improve the efficiency and bring all of those things down to our embedded devices. The core layer between machine learning algorithms, sort of the research side and the actual hardware, and then is the software tools and the state of these tools, both for inference as well as for training. Because no matter how great my research are, it will never run fast on a device if the ecosystem or if their inference stack is not there and not supported. So we're seeing great advances in here. In general, there is a bit of a chicken and egg problem here because the rate of iteration is very different between all of these three categories, whereas hardware can be quite slow to iterate on. It takes a time scale of years and sometimes even more. And ML algorithms are published every day, almost every hour. So to fix this and actually go further and really push the frontier, we need to have co-design to find the most optimal solutions. And if you want to learn more about this, there's a great paper, the Hardware Lottery, which discusses a few of the subtleties in this, where machine learning algorithms progress in a direction where there's hardware available, where hardware progresses in the direction what's currently used in practice. So we want to break this and in this talk focus about what we can do on the software and the algorithm side. And I will introduce to you binarized neural networks, which is a form of extreme quantization. So binarized neural networks are essentially neural networks that are quantized in an extreme way. And for quantization, I think most of the people here in this talk who have, for example, followed the tinyML book or have worked with TensorFlow Lite for microcontrollers are familiar with the process of going from a full precision 32-bit model to an 8-bit model. What this does, quantization, we map a set of often almost continuous values to a much smaller set and reduce the precision. In case of 32-bit to 8-bit, this is rather, I wouldn't say trivial, but it is very common in And today you can do it with next to no loss, either during training or after training. What's currently more exciting and a bit more difficult is going further. 2-bit, 4-bit, 2-bit, and then even 1-bit, where crucially, if you visualize it, you lose all information about a magnitude of your weights in your neural network. So why are we actually doing this? Why are we interested in going below 8-bit precision and going all the way to actual binary? This is not because we just want to make our lives more difficult, but we actually get true advantages over that. So we have a large memory reduction if we reduce the precision used by a neural network model. And in the case of 1-bit, value is 32, uses 32 times less memory compared to a floating point model, which means 8 times less than commonly used 8-bit models, which is quite large. So if we're looking at models that are commonly used in computer vision for image classification or object detection, convolutions are ubiquitous. Almost all of the models used in computer vision use some sort of convolution in the inner parts of the network. So if we look at what a binarized convolution is, we have here visualized a floating point or like an 8-bit high precision convolution, just the inner loop of it. So we have on the left incoming a patch of the activations that are convolved with just a single filter, and this is just the inner loop. I don't think I need to explain the mathematical details of what a convolution is. But essentially, the inner loop does a multiply and element-wise multiply and an accumulate to reduce this down to a single value and capture the correlations in there. So for the case of binary, what does this mean? We now have binary activations and binary weights. Those are getting multiplied as well and then accumulated as well. In binarized neural networks, usually we represent weights and activations as floating point -1 and floating point +1. So a 0-bit in memory means floating point -1, whereas a on-bit, a 1-bit means floating point value +1. So what this allows us to do is actually replace the multiplication and the accumulation part. So 2 instructions or 2 operations that are quite difficult to do on hardware very fast, and replace them by just XNOR and pop count, which can be implemented very efficiently on custom silicon or on FPGAs. So if you now look at this image, and if you trained neural networks before, this might be a bit counterintuitive. So in the process of training neural networks, it's all about taking multiple gradient update steps along a gradient descent landscape and slowly updating and accumulating the progress in this way in weights during training. Now, when weights are all binary and activations will be binarized, we have 2 problems. First, we cannot take small steps in a gradient direction because weights can only be -1 or +1, so can only flip a weight. And secondly, we don't even have a gradient because the sign function of going from activations to a floating point activation to a binarized activation requires a sign function which is non-differentiable at -1. So we really have a problem there in training those networks, but we still do train those networks. So how? And the way it's commonly done in literature that was proposed in I think 2016, binarized neural networks are still quite a new technology, is we represent the binarized neural network as having latent underlying floating full precision weights that in the forward pass are binarized, and in the backward pass we use a straight-through estimator to approximate the gradients. This straight-through estimator is essentially just a fancy way of saying we ignore the binarization in the backward pass. So we have inherently some uncertainty also in the gradient direction here. For the activations, we do a very similar thing. We binarize in the forward pass and again ignore the sign function in the backward pass and replace that with the clipped identity, the straight-through estimator. And doing that, we can still do gradient descent, use your favorite optimizer, and train these networks, and they actually converge and can do useful things. So if you want to learn a bit more about binarized neural networks and about what's actually going on under the hood, we published a paper 2019 at NeurIPS, which sort of challenges this assumption of underlying latent weights and presents a new method of optimization, which fundamentally looks at the counterintuitive nature of BNNs being we take small update steps and accumulate weights, but the only actual thing we can do is flip a weight or don't flip. So I think that's a nice read if you're interested in a bit more literature. So if you recall my slide before where I talked about efficient deep learning or efficient machine learning requires advances in the entire stack. This is now the machine learning part or the research part, where papers are published in arXiv. But the glue, the actual bringing it into practice is still missing. And neural networks or in general ML algorithms are only as good as when they can be used by practitioners for real applications. So we published an open source ecosystem of BNN software, which consists of 3 parts. First one is Larq-Zoo. It's a model zoo of ready-to-use pre-trained models covering both state-of-the-art models on ImageNet as well as commonly used models in literature, which is great for researchers who either want to get started in the field and explore what's out there, or researchers who, for example, want to develop a new training algorithm and want to build on what's currently out there without needing to spend hours and hours trying to reproduce existing literature. Larq itself is a framework that is built completely on top of TensorFlow Keras. We aim with that to be as intuitive, as flexible as possible, and provide complete compatibility, which makes it easy for people to adopt and to try out without needing to learn an entirely new tool or entire new set of ideas. I'll show later a few code examples of that. The second is the third is Larq Compute Engine, our optimized runtime for benchmarking and running neural networks on commonly used devices. So for Larq, if you're familiar with TensorFlow Keras, this should look simple to you. This is just a plain model. And the great thing about being compatible with TensorFlow, being fully compatible, is that we can replace just every Keras layer with a Larq layer and can recover the same neural network. meaning I can still use this model with distributed training on GPUs, I think even TPUs, and do all the great high performance stuff. And if we now want to transform this into a binarized neural network, we can simply add a quantizer, kernel constraint, and an activation quantizer, which will implement a trivial binarized neural network similar to the one I showed you earlier. Of course, you can customize every part of this to your liking. Use your own training algorithm, use your own quantizers, name it. So with this in mind, we did research for a while, and there was still one piece missing, and a large body of work also in machine learning on Archive or so is developing efficient model architectures and benchmarking them on theoretical metrics like max and the memory footprint. So we developed Larq Compute Engine in order to really facilitate the research both internally as well as externally, which provides a highly optimized open source inference engine based on TF-Lite, which again follows the notion of being fully compatible and easy to adopt for anybody who wants to try it. And it runs on commonly used devices that are available in research labs, like Android phones and Raspberry Pis. It's optimized for the ARM v8a instruction set. And yeah, so and there will be a paper published about that in MLSys. I think it's already available on the archive link below if you want to check it out. As part of this paper, what we did is collected all of the models, all of the dots you see here are commonly used models, binarized models that are trained on ImageNet, and that are common in literature. We've taken them straight from our models to deployed them with a few lines and benchmarked them. And using this knowledge, we're able to develop QuickNet, a nice architecture, which we're very, very happy here outperforms sort of current models that are used in literature. So I talked a lot now about the software side and how to train a BNN and how to develop BNNs. But I'm here today at tinyML because we want to show you something on microcontrollers. And this is we will do this with later with a live demo, which I'm really excited about. We are looking at the task of person detection or visual wake words. Task is rather simple. I get an image of a microcontroller, and the network should decide whether there's a person or multiple persons visible, or whether there's no one visible. So this can be used in practice quite a lot. For example, since we will deploy this on a microcontroller, things like detection whether somebody is in the room, how to control heating, whether to turn on a TV, or to actually have this as the first stage that triggers a part of a larger chip or a larger neural network that will do further analysis just in cases where there are people visible. So we will show a demo later on a board, on the 32L4 development board from ST Microelectronics. I have it here, which is a great little board to do development on. We choose this. It has quite a large amount of RAM, which is not necessarily necessary for the models, but it is quite useful while you're developing and while you're sort of debugging and trying to explore your models here. It features a very commonly used ARM Cortex-M4 core, which is clocked at 120 megahertz. And for it, we attached an Omni vision camera, which has 1.3 megapixels, and which we will use for the demo later on. So we developed a model, a binary model, to solve this task of person detection. And we're showing here some benchmarks against a commonly used MobileNet V1 0.25 model. This is benchmarked on the visual wake words dataset, which is a subset or modification of the MS COCO object detection dataset, and benchmarked this on an ARM Cortex-M4 CPU. This is a slightly faster CPU for the plot here. It's from the F4 board, but you will see the demo later. So if we bring together what we've learned about how to build an efficient machine learning solution, we talked a bit about the hardware, but today we focused on the algorithms, in our case, Binarized Neural Networks, and the software and the tools, our here proprietary inference stack of to run BNNs efficiently on device. But I think I forgot one of the most important parts, and actually the important part why ML and machine learning and deep learning is so booming, and this is data. The real power of deep learning comes in when you have both control over your data set and your data pipeline, and are able to do analyses and really understand in which environment you're deploying your models and in which environment they work well or don't. If we're bringing these models on device and actually want to have them work in real life as part of a product or as part of a demo, most papers, and we do this as well in our papers, look at model accuracy. It's a nice metric. It is tested on a research data set, and you can very objectively or seemingly objectively compare different models. But in the real world, there are a few more things that we care about, and most crucially, it's consistency of prediction, and which means also the generalization to different lighting conditions, and crucially, robustness. This means robustness against perturbations, robustness against different artifacts that might come from the camera or from the environment where the model is deployed in, and also robustness against shifts. For example, on the right, you see an image where a model is trying to predict whether there's a human in the frame or there's no human in the frame. So a green border means the model has detected that there's a human, whereas the red border means the model has detected there's no human. So for us, these two images who flick back and forth look identical or almost identical. What we did is we just shifted it by 1 pixel to the right. For a human or for a person, there's next to no difference visible. But the model completely fails and thinks there's no human in the frame just because we shifted it a single thing. So all of those things are tricky and are very important to get right in cases where you want to deploy BNNs or any model in the real world. So where do those problems come from? So there are a few different things in that, or a few different problems with this, and one is that commonly used research data sets do not really capture the data distribution that we care about in the real world. This doesn't mean these research data sets are bad by any way. Visual wake words data set is a great data set, and ImageNet as well. It really facilitated the boom in models and by providing a stable benchmark. But oftentimes, or for example, in the case of visual wake words data set, those images are, or the COCO data set, those images are collected from Flickr and from oftentimes very different environments compared to where we would actually like to deploy our models. So we will later show you a demo of person detection in an office environment, whereas the MS COCO dataset, which is commonly used to train those tinyML person detection models, usually has quite a lot of images of people doing sports outdoors and negative examples taken from wildlife or cars or planes. And this means we can train a good model, and we've shown that a few slides ago that this works quite well. But the model doesn't really work as best as it could in the intended environment. Also, the cameras for the microcontrollers can sometimes be quite different to compared to the cameras used to capture those data sets where they're taken with big DSLRs. So all of those things need to be taken into account when we want to bring something into the real world. So how did we solve this internally at Plumerai, or how are we aiming to solve this? We've taken inspiration from the software industry, and they're having developed many great tools and to test and verify software that it works correctly and crucially keeps working correctly. And we want to do the same for deep learning, especially in an embedded environment where we might not be able to do live A/B testing with stream predictions and constantly analyzing our model, but where we want to do that beforehand and really be comfortable actually sending those models into the real world. So this concept of unit testing, or just in general regression testing, we start this process of identifying and analyzing our failure cases. So let's say I have a model, I downloaded it from the TensorFlow repo, or I coded it up myself, or read a research paper and re-implemented it. And I have some sort of baseline. It gets great predictions in some cases. In some cases, it has issues. So what do? We collect different examples of cases where it fails, and really try to analyze it, why it fails, and why it doesn't recognize or doesn't work correctly. And for example, on the left, you can see that we did some analysis using saliency maps to analyze where the model is exactly looking at. And this can help to identify the reasons behind failures. For example, we had cases where we got false positives because there was a desk chair there. And in the data set we used to train it on, desk chairs always meant there was a person in the frame. So the model thought, okay, when there's this chair present, I will predict there's a human in the frame. And doing this analysis, we wrap this up into a test case, and then we move with this knowledge to the second stage, which for us consists of collecting labels, collection of more data of similar examples. So I go out, or I scrape images from a publicly available source or data set, label them, and have therefore an extended suite of examples for this particular unit of test. So with this collected data, we can do two things. We can do more tests to sort of verify that our analysis was correct, and we can use it to train models. And and retrain and therefore go into the third stage where the usual model iteration of researchers or engineers trying to improve the model either by feeding it more data of critical cases or doing augmentation, for example, to get rid of this shift issue. And the fourth option is probably one of the most important ones, and then is that we take our model that we think is an improvement and verify it against all the previous unit tests we have collected, and make sure that we don't regress in a completely different case or environment. And if we go around the circle enough times, we hopefully have a model where we feel comfortable using that in practice. So we did that, and we did that for the person detection example. And we will show you now for the first time running a binarized neural network on those little microcontrollers. I said model accuracy doesn't really equal to real-world performance. So how can we show you that we actually do something good, or that we are showing you something that is truly state-of-the-art? So we compare it against the MobileNet V1 baseline. This is a model that is just straight taken from the TensorFlow micro example. This was trained on the COCO visual wakewords dataset and is running on TF Lite for microcontrollers. It has on this particular board a latency of around 700 milliseconds, which is usable in practice, and a model size of around 300 kilobytes. And we will compare this against our own binarized neural network, where all the three parts that we identified of how to design a efficient machine learning model, having good software, having good machine learning algorithms, and having an understanding of the data. We deployed that using our internal inference stack for microcontrollers. This stack is leveraging TF Lite micro heavily for everything that is non-binary. And we achieve very similar latencies to MobileNet. It's a bit slower, 850 milliseconds latency at a model size of a bit more than 100 or 150, 15 kilobytes of model size. So I told you a lot of numbers, but I think this can be actually better shown live. If this would be an in-person event, it would be great to do this on stage, and so you can experience that. We're trying our best to do that to get you a live experience. So I'm very pleased to introduce to you our CEO and our co-founder Roland, as well as my colleague Koen, who is leading the research team. They're currently in our Amsterdam office and will show you the live demo of those two models compared side by side, running on the Cortex-M4 microcontroller board.
Hello, everybody. Thank you very much for the introduction, Lukas. I'll now switch to our other camera. So this is the room that we'll be using to showcase our person detection demo. And this is the discovery board that we're using, the STM32 discovery board from ST Microelectronics. Right now it's running a TensorFlow Lite micro model MobileNet. Couldn't put it down.
Okay, so since we will need to have some set changes in the office, I will be narrating this demo. And as before, you see when there's a green border, the model detects a human. When there's a red border, the model doesn't detect a human. So again, this is MobileNet that comes with, or that is from the example of TensorFlow Lite from microcontroller. And this is a distance test. So we have a room of around 11 meters, and we see the model recognizes Kuhn quite nicely when he's close, but when he's further away, you really see that the model stops recognizing him, which is obviously not really good. If we then switch to our second case, where we have a normal desk set up, Kuhn needs to do a bit of reordering of the set. This is all live. And what we will, what I'd like to you to observe mainly once we see the microcontroller again is the stability of the prediction. We're really looking for are there frames where the model detects has false positives or false negatives. So here you see nobody is in the frame, and the model also correctly doesn't predict if somebody is in a frame. But now Roland is sitting down and it doesn't recognize him at all. If he's going behind the desk, it really has troubles. Only when, I think when he's fully visible, like when he just walked out the frame, the model correctly detects him. This flakiness is not really nice in a real world example. So we want to compare this against our SpiderNet model or our Plumerai binarized model. And for that, we will use the same microcontroller. To note, this microcontroller is not attached to any computer or anything, so everything you see is running directly on the board. Kuhn is now flashing the new model onto the device, which means he's connecting it and getting our model on there. So we'll wait a few seconds once that's done. I want to reiterate that this is quite special. This board is very low power, has a tiny CPU, and this is if this works correctly, we can be very happy. So this is now our model, and the microcontroller powers on, which is a nice logo. And we have the same scene as we had before, or close to the same scene. We see no human present in the frame, no false positive. And as soon as Roland walks into the frame, sits down at the desk, he is correctly detected by the model. So in previous cases where MobileNet had troubles correctly recognizing him was when he was moving around in the chair. All of those areas seem to work correctly, and it work also with a mask. And as well, if now Kuhn enters the frame, we can show that it also works with multiple people, which is great. So this is not dependent on whether there's only a single person visible or not. So if we now switch back to our second scene, where we before did the distance test, I think here the difference is the most apparent. This is, we try to our best to utilize the full length of the room, which is why we need to do a bit of set redecoration. So this is again the room, and what we will hope to see is that that Kuhn will be recognized all the way to the end, and we can show that the person is detected correctly. So this is now our model again. Kuhn enters the frame. We have stable predictions. And the great thing all the way at the back, even though Kuhn is quite small in this frame, we have stable predictions of him. If he sits down now, this also works. We will just let it run for a bit longer, and I think the difference here is quite clear. And what we hope to show you is that yes, binarized neural networks can actually run in practice and can give correct predictions and can be used in real-world applications. So that's it from our Amsterdam office. Thank you very, very much, Roland and Kuhn, for doing the demo. We will now switch back to me to finish the demonstration, the presentation. So what did we show? We showed our binarized neural network that was trained and deployed using our internal inference stack, and showed how we can utilize data to really improve model performance. This is the full entire solution covering the inference stack and also the research side. So we're really proud that this is now for the first time binarized neural networks running on a microcontroller. So I stressed the fact about hardware very early on in the presentation, and this is a point of interest. So for example, we are now running this on a Cortex-M4 microcontroller, which has great capabilities to accelerate 8-bit convolutions, for example. What's next for us? We want to bring this to more platforms and do low power inference on very low power FPGAs using our Plumerai IP core for BNNs, which we've developed internally, as well as running it on an extended RISC-V CPU, which then has instructions directly to accelerate BNNs. We have also partnered with XMOS, who gave a call a few weeks, gave a talk in this venue a few weeks back or a few months back, and we're excited to bring binarized neural networks onto their platforms, all platforms that are much more advantageous to running BNNs compared to the microcontrollers we showed. So we're really happy that even with current technology and current hardware, this works as well as it does. In terms of tasks, we're working obviously expanding what we're capable of doing from eye gaze detection, but most importantly also person localization with bounding boxes. And this can be useful to count the number of people present in the scene, and can be deployed either on real tail or in different other areas where detecting people and localizing them is important. We will show this in the tinyML summit, which will be held later next year, later this year, sorry. And we're really looking forward to do that and see what's possible in the future once we expand both on the hardware task and also keep continuously improving our technology there. So this is the end of my talk. We were very happy to bring deep learning to all edge devices and show for the first time binarized networks running on low power hardware. As always, this is we will continuously improve this and expand that to different areas. So my name is Lukas. You can reach me at the email or have general inquiries at hello@plumerai.com, and I'm now very happy to take questions.
Thank you so much, Lukas. That was a fantastic presentation, and we actually have a ton of questions. So they've been upvoted by our audience, so I'll go in order of how many upvotes, and then I'll pass the questions along to you after the session in case there are any left over that you could answer in our forum. So our first question here is, how does binarization work with recurrent models? Are there any experiments or results on that?
So we internally, we've done mostly work on computer vision using convolutional neural networks. There have been papers published on using binarization on recurrent neural networks. But I don't have first-hand experience on that. But there have been papers running BNNs or using binarization on, for example, LSTMs or GRUs effectively. Yeah.
Thank you. So second question, what's the performance and computation gap between intake quantized and binarized neural networks?
So this is a very good question. And this cannot really be answered in all generality. This depends very much on the type of hardware we use. So in research papers, often the term of 64x compared to float 32 is used, which is the number of the sort of the area size like the transistors would take up if you would put it on a chip. For the exact numbers, this very much depends also on the model. So I cannot really give you an exact number out of my head, but we can get back to you on that and answer that in the forum later for what's that on our microcontrollers.
Thank you. So next question, how are the other parts of BNNs binarized besides dense and conv operations?
So one thing that I didn't mention in the slides is we're talking about binarized neural networks. We usually still have full precision operations in there or higher precision operations like int8 or so in there. So usually we have a convolution and then followed by a batch norm. This can all be fused together in the kernels. But for first and last layers, like if you imagine for a prediction where you do regression instead of classification, you actually want to not just have -1 and 1 as an output, but also pass it through a softmax. And those layers generally are either int8 or float 32. So also the model we showed there, the first layer is int8, which takes the image and sort of expands it into a larger feature set. And then we actually use binarized convolutions in there. So I guess the answer is they are not binarized. Many different parts of the network are still higher precision, and that's okay because we only aim to binarize the parts that are crucial and take up the most computational energy in the models.
All right, next question. By ignoring the activation during training, aren't we ignoring the non-linearity that gives the extra flexibility of our model to learn complex relationships?
Yes, very good question. So we sometimes can still use a non-linearity in there, and this is something we actually do in practice quite often. So, for example, you have a deep neural network, and we do a ReLU and then a batch normalization in there. But in practice, this also works if you don't have the nonlinearity in there, because if you think about it, even though the sign is probably a very bad activation function for a general network to use, it is also nonlinear in its extremist form. So this acts as a nonlinearity as well, but you can also combine it with other nonlinearities, and this is what we do in practice, yes.
Okay, thank you. So another question, how useful are BNNs for VLSI or FPGA implementations as compared to an implementation on a microcontroller?
Yeah, excellent question. So they're actually a lot better on FPGAs or on chip. So for example, what's on the microcontrollers, you have fused operations to like a multiply and accumulate that can efficiently do int8 convolutions. And if you are putting binarized neural networks on FPGAs or actually on a physical silicon, well, on an SoC, you can take advantage of the fact that we can replace multiplies and accumulates with XNOR and pop count, whereas on microcontrollers, for those things, we need separate instructions, which add latency compared to the most optimal way. In terms of memory or so, that very much depends on your implementation, but also on the microcontroller, we get some efficiency gains just to the fact that we need to read less memory and to the fact that our weights and activations are lower precision.
Okay, so I think we've been through all of our highest voted questions. And so I'm going to send you the rest of the questions and you can answer on the forum after the session. And we'll be sending out a link to all of that in a follow-up email to all attendees. So I think now it's time for our wrapping up messages. I'd like to give another thanks to our tinyML Talk sponsors. So we have our strategic partner, ARM. We have DeepLight, Edge Impulse, where I work, Maxim Integrated, Kixo, Reality AI, and SynSense. And again, if you'd like to sponsor, please contact Betty at tinyml.org. We have a slide from our sponsor here, ARM, who are the software and hardware foundation for tinyML. So you can reach ARM on all of their social media, on ARM Software Developers on YouTube, ARM Software Dev on Twitter, and they have some really great ML resources on their developer site. DeepLight use AI to make other AI faster, smaller, and more power efficient. Thanks to DeepLight for being one of our sponsors. At Edge Impulse, we make tinyML accessible for all developers, from embedded through to AI engineers. So you can get a free account to build and train and deploy models at edgeimpulse.com. Maxim Integrated, new Max 78000, implements AI inference at over 100 times lower energy than other embedded options. So now the Edge can see and hear like never before. Kixo's AutoML for embedded AI provides an automated machine learning platform that builds tinyML solutions for the edge using sensor data. Reality AI is for building products, and you can check out their systems at reality.ai. SynSense builds ultra-low power, sub-milliwatt sensing and inference hardware for embedded mobile and edge devices. We design systems for real-time, always-on smart sensing for audio, vision, IMUs, biosignals, and more. Our next tinyML talk is going to be on Tuesday, February 2nd from Martino Sobaro, and he's an R&D scientist at SynSense. And the topic is always-on visual classification below 1 milliwatt by spiking convolutional networks on Dynapse CNN. So the start time for that webcast is, as usual, 8 a.m. Pacific time. And if you have a talk you'd like to suggest, please contact talks@tinyml.org. Thank you, everyone, for attending. Thank you to our great presenters, and we will see you next time.